Did it work? Oh, okay. And is the audio still bouncing? Alrighty, so so we're interested in solving systems of differential equations, all right? That's what we're after here. Let me show you an example of one. For example 8 for today, yeah? We could have something like dx dt equals to minus y and dy dt equals to x. This is a system of two differential equations, all right? In fact, I can put this in matrix normal form. So matrix normal form would look like this. Well, more to the point, it's d dt of xy equals to, in this case, 0, minus 1, 1, 0, xy. There you go, matrix normal form. Probably tomorrow I'll show you how to solve this using a technique. But, you know, one of the ways you can solve differential equations is just by sort of brute force substitution. So can you guys, I bet you guys, without me blathering on about solution techniques, you probably could solve these yourself already, right? How would you do it? There's a common sense approach here, right? What's that? Oh, solve for dt? Oh, that's interesting. That's, you know, your method is, I mean, you're like to solve both for dt, I think is what you said, right?
Yeah, I said both equal to dt.
That's really nice, Isaac. What you're doing is called the method of characteristics. That's unfortunately forgotten for most people. Like if you hadn't said that, I'm not sure I would have covered this semester. Thank you. But it's actually a totally legit way to solve this. I mean, that's exact. So we got like x squared plus y squared equals to r squared. Those are our solutions. Our solutions are circles. Very good. But that's not the kind of solution we're looking for. Because our solution should actually be two functions of time. So what we just found by doing what we did in blue is the level curve, which is parametrized by the solution that we actually want. But that's the valid solution technique. It just gets you to a different place than we want to go. That's all. But you got the right kind of idea, which is substitution. How about this? If x is equal to dy dt, dx dt is what? dy dt, right? It's ddt of dy dt, right? And that should be equal to minus y, right? So you see what we have is we have y prime prime equals to minus y, aka y prime prime plus y equals to 0. And so we can solve how? Well, y equal to c1 cosine t plus c2 sine t. Because this is lambda squared plus 1 equal to 0, the solution is plus or minus I. That's our solution. And then what's x? Well, that's easy. X is dy dt, so I just differentiate that. And x is equal to minus c1 sine t plus c2 cosine t. And there you go. There's our honest to goodness solution. It may not be quite as obvious that those are circles, though, huh? I mean, you could repackage this as y is equal to a sine of t plus a phase angle phi. And then this would be, you know, a cosine of t plus a phase angle. And then it would become quite obvious that we're looking at the solution. The solution has radius a, and it's a counterclockwise oriented circle. There's some choice of C1 and C2, which will rewrite the solution as a times sine plus a phase angle. I'm pretty sure. Okay, so what if we were going to solve let's look at another one. Example 9, we might have x prime equals to 3x plus 2y plus z, y prime equals to x minus y, and z prime equal to 4x plus 6y plus 8z. This would be what? This would be a system of 3 differential equations, right? And you could rewrite this in matrix normal form, like so. And so we got what? We got 3, 2, 1, 1, minus 1, 0. So what's the last row? Can you guys tell me? 4, 6, 8, yeah. So there you go. I put our matrix, I put our system of differential equations in so-called matrix normal form. So this is still called the matrix. This is called the matrix of coefficients. Now, how would you solve this? We could do substitution and elimination, right? You can take these differential equations, you can solve, like the first one, we can get x is equal to y prime minus y. So I can eliminate x in terms of y and its derivatives in the other 2 equations, right? And then I could try to take some linear combination of the x prime and the z prime to eliminate another variable. You can do that, right? But we don't want to do that, right? In chapter 5, he describes a somewhat systematic method of elimination in terms of operator notation, all right? I don't usually cover that much. That's more or less what we're doing over here. I call these to me, this solution is an ad hoc method. It's just kind of by the seat of our pants and just kind of have an intuition for what we should do and just try. We want something better than that, right, as a solution technique, and I'm going to show it to you. But make sure that I don't feel bad about today. Example 10. How about this? What if we have y prime prime plus y prime plus y equal to e to the x, and we have z prime prime plus z equal to cosine of x. The problem is to write this in matrix normal form. Okay, so I haven't really carefully defined matrix normal form yet, but I'll tell you what that is right now. Matrix normal form is this. It looks like dv dt equals to av plus f. All right. You got to find a matrix of coefficients, a vector of variables, such that we rewrite our system as a system of first-order differential equations. You're like, but these are second-order differential equations, right? So let me show you how we do it. We say y equals to x1. We say y prime equals to x2, right? And that reduction of order trades this second-order differential equation for 2 first orders. So like if y is equal to x1, what's y prime? Well, y prime is x2, right? But it's also x1 prime, so x1 prime equals to x2. What's y prime prime? It's e to the x minus y prime minus y, aka e to the x minus x2 minus x1. So that, folks, that's my x2 prime. See, so I traded my second order differential equation here for these two first order differential equations. And you can do the same thing with the second differential equation with the z. Introduce an x3 and an x4. So I'll let z equal to x3. What do you think z prime should be equal to? x4, right? So x3 prime is x4. What's z prime prime? Z prime prime is cosine x minus z, which is cosine x minus x3. And that, of course, is my x4 prime. So I've traded my second order differential equation for these two first order differential equations. And so altogether, we can write x1, x2, x3, x4 prime oops. I'll do the first row. The first row is going to be 0, 1, 0, 0, and a 0 over here as well. I'm getting that from x1 prime equals to x2. What's my second row? The second equation underlined in green, how does that translate over there to the matrix? Have you guys figured it out? Maybe it helps me to write this x2 prime minus x1 minus x2 plus e to the x. Maybe that helps you. I don't know. What's my second row? Mm-hmm. 0, 0, and then, yeah, we got an e to the x over here. My third row is 0, 0, 1, 0, I think. Oh, wait a minute. Oopsie. X, what is it? This is the fourth one, right? So it should be 0, 0, 0, 1. That's my first red underlined equation there. There's no inhomogeneous term there, just a 0. And let's see here, x4 prime is what? No x1 and x2, right? So I get 0, 0, minus 1, 0, and then a cosine x over here. So this is my v, my vector of unknowns, x1, x2, which in this case is y, y prime, z, z prime, right? And this is my matrix of coefficients A. Here's my inhomogeneous term, F. So let me just make a claim. If we take any system of linear differential equations, all right? In other words, take a bunch of linear differential equations and just think of them together as a simultaneous thing. It's always possible to introduce new variables so that that given system reduces to a bigger system, possibly, with just first order differential equations. We call this system matrix normal form. So what I'm showing you is that if we can solve dv dt equals to av plus f for any a, then that's it. In other words, all other linear systems can always be recast as a system of first order differential equations. So if we can solve the first order problem, we've got everything done. So tomorrow, I will show you how to solve pretty much any first order differential equation. But again, we have to be limited to the case that A is full of constants. If you put functions in A, that is not nice. Anyway, I mean, we can solve some of those with Laplace transforms later, but you want to hit it there.